Okay, in this video we are going to talk about our second homework, which is to build and to train a generative language model that can generate some natural language text or programming language code. You will have about 2 weeks to complete the job. So first of all, you have to decide and collect your dataset. Because we are using a self-supervised algorithm, so we don't need any labeling. You don't need to do any human labeling at all. All you need is a bunch of raw text. Our goal is to train our model to generate some text that is similar to the raw text that provided as the training data. Because I wish you can judge the quality of the generated text. So the language data that you are using as training data has to be the language that you are familiar with. Otherwise, you will have a hard time to judge how good is the text generated by your model. So if you cannot judge the quality, you cannot tune your model. Okay, then the model, the only I think the only other requirement for the model for the training data is it need to have a decent size, a decent amount of sentences in the dataset. If it contains just like 100 sentences, the model may be overfitting too easily, and you may provide too little information for the model to generalize the results. So it would be a good idea to have a model that has at least 5,000 sentences. However, this number varies depends on the language itself. So for example, Chinese and English are very different. Chinese has thousands of characters, while English has, even if you consider all the capital letters, all the small case letters, and even some symbols, you may have just have 100 or maybe 200 characters. So that makes difference. So you may need different number of different size of dataset, depends on your language or the text content in the dataset. So in the lecture video, we have give some information that is a collection of the training data of large language set. So it is a good idea, it is a good timing that you can try a few of those datasets listed in those repo. Because sooner or later, you might have to train or fine-tune some large language models. So it is good if you have some familiarity with those datasets. So you can download or try part, because those datasets are often very large. If a data is too large, it is very difficult to train. So you can download part of the dataset. Or if you don't wish to do so, there are a lot of text data presented, or you can find in the web. So you can even sometimes you can crawl from some web page, or you can download legally from, say, Wikipedia. Wikipedia has some archive options, so you can download the whole Wikipedia into one file. You may need to have some algorithm to extract the raw text from the because Wikipedia is in XML format, so need some algorithm to do some coding to extract raw data from the archive, but you can do so. And there also has some Wikimedia and Wikibooks, or if you have other source of a decent amount of raw text data. Maybe if you have your own blog site, or if you really use the social media a lot, maybe you already have some text that is readily provided so that you can use as a training data. All you need is just collecting as a raw data, a raw text data. Okay, you don't need to provide any evidence or anything right here, but you have to start from somewhere. You have to actually have some data set, so this is some just instruction. Then you are going to train two different kind of models. First is the simple one that we actually discuss in our lecture videos. Is you simply collect or calculate the statistics, the conditional statistics from your data set. So for each sentence, for your data, you just simply from every piece of the data, for consequent letters, for consequent characters, you wish to predict the next one. So you you find out the statistics from the training data, and just like we introduced in the lecture videos, you are going to store the information into a dictionary in Python, and maybe in some counter. So try this method with two different kind of n. So I suggest if you are using English, maybe you are trying the length of 10 or a length of 5 and see a difference. Okay, and the following bold steps are requirement. You need to provide all these informations in your GP notebook that is uploaded to our E3 system. So first of all, the B, C, D parts are simply try to explore some data, some information from the statistics that you are collecting from your training data. So I need you, so these are just some simple questions that you can answer from the statistics and the information collected from the training data. So the first one is the B part, is how many distinct couples has been collected. So of course, if the n is just 5, and when n is 10, so the larger the n is, the more distinct tuples you will have. So just show me the information of in a notebook to see how many tuples is contained in your statistics, and then find out the most popular tuples that appears in the data set. That is the most common consequent letters of consequent characters of length n. So find the single one most popular tuples in your data set. Okay, then for this data set, then tell me and show. When I say show, it always involves some code. Also, you have to write some code to find out the information. Okay, so in this one, you have to find out the top 3 candidates that is most likely to appear right after the above tuple. Okay, so the B, C, D part are required to be shown in the notebook, and you have to mark this one is B, and what is the answer of this one, and what is the answer of C, and what is the answer of D, and do this for two different lenses. And for the final one is to actually generate some text. So you can do any way to using your model to sample. I mean, anyway means you can have any kind of prefix because we are using an autoregressive model. So you need some prefix to generate your model. So you can use any prefix that is suitable to generate 3 paragraphs of text. There's no requirement or limitation of the length, but I suggest you to generate like 200 or 300 characters. That would be suitable. Okay, so basically this part is the you can actually have some reference to the Jupyter notebook that provided by in the slides, in our slides or in the lecture note. However, you have to, you should code, type everything by your hand. Do not just copy everything in the notebook. Write your own code. So at least you have some different names or different structures to do this part of like collect the information, to do sampling, to do everything. So it will have some difference. So do the best you can without simply copying the notebook. Okay, after you do this, the second one is to replace the counter by a neural network. So you can use any. You don't have to use RNN if you are not familiar or are not comfortable with RNN. You can use any kind of different neural network, which I will show you a little bit later in this video. So in this part, you can use the same data above, or you can use a new one. So for example, you are using a Chinese language dataset for the first one, but you find it become difficult for the second part if you are using the same if you are using the same dataset. Then you can change your dataset to another language or another because it is totally fine, because you are using two different kind of models. These two different models have different properties and can solve different problems. So although if you are using the same dataset, then it might be good because you can compare the differences between the first model and the second one. However, I think at least in the homework, I am not asking you to provide such information. I encourage you to do so, to compare the difference between these two. But the whole point for the second part is more like to familiar or to warm up about the deep learning frameworks. Because not all of you are familiar with deep learning frameworks. So in this part, you have a chance to kind of familiar with one of the deep learning framework. So even if you are familiar with, say, PyTorch, you might not familiar with or used to deal with the sequential data. You might have some experience for dealing with images or maybe even like audios. But right now, we are dealing with some sequence of text. So that might have some differences between images and the text data when you are trying to build your data pipeline. So this one is a kind of warm up to give you a chance to practice or think about how to do it. So for this part, you can use any model, any data pipeline, and all you need to provide is to generate 3 paragraphs of text, or maybe some code of some program language, like the Linux, C++, things. Okay, so let me show you some example of what I did, and you can compare with the lecture videos that is discussed as the implementations. Okay, so let me let me show you the remote. So I did my coding on a different computer. Also, this one is the computer. So first of all, the data I'm collecting is from some large language dataset. Some dataset for training large language models. It contains some academic papers, some paragraphs of academic papers. So first of all, what I'm doing is to do the simple Markov chain of order kind of models. I'm only using, so first of all, I'm only using like 20 sentences from the dataset. So let me show you the data set itself. So let me print this. I don't have to. Do I have to? Oh no, I can print this tag. So you can see. Let me show you the first like 3 sentences. So these are the text. So you can see it looks like, although this has only 3 paragraphs, each paragraph contains like 10,000 characters. So it is a longer, in long format. So each one looks like academic writings. So you can see the experience and all of those things. So I'm trying to use like for the demo purpose, I'm using using the first 100 samples, which may contains it is. I should remove this line. Okay, so let me just use the first. Do I print anything? So did I? Maybe I should interrupt it. Let me do it again. Okay, so this one is actually has in a JSON format. So I will have to. It is not in raw text format. It actually contains some metadata and some labels, but I'll only use the raw text part. So you can see that when I read each line, it contains a lot of lines in this dataset, and each line is in a JSON format. So I load each line from the file, and only use the field because when JSON read it, it reads into a dictionary. So I only use the text part of this data. And instead of using some tricks using the list slicing, I use the dequeue data type. This one is a queue that has a max length. So if you push more things into it, it will discard the older ones. So let me do some simple example right here. So this one is in standard Python. So let me just let this queue to be the queue max line to be have like 5 characters. So let me do a simple loop for I in range 10, and I will append I into Q and see what Q will be. So you can see it kind of like standard list at the beginning. So when I append 0 into the list, it will contain 0, and append 1 into it, it will append at the end of the queue, and so on until I have 5 elements in this queue. So if I push append one more element, which is 5, into this queue, the 0 is going to be discarded or push out from the queue. And if I put one more element into this queue, the oldest one, which is 1, is going to be discarded. So in any time it will contain only 5 elements. So that is exactly what the queue is designed for. So I'm using it instead of using some slicing tricks in Python. And I am presuming that the queue is efficient enough. So I'm simply using a queue to do so. So in this text, for each character in T, first of all, I wish to do some statistic to see how many characters, different distinct characters, are in this dataset, because I have no idea. It certainly doesn't just have some. Let me show a T to you. It certainly doesn't just have English letters. It contains like some symbols. I don't see it here, but it. Let me simply to put it out. You can see it contains a lot of different symbols. So if you use more samples, I only like 100 samples here. In some text it contains some foreign languages, like in Chinese, or maybe in other, like French or Spanish. I'm not sure, but it certainly doesn't just contain like some English letters and digits and some common symbols. It contains a lot of unexpected characters. So I use this one to kind of observe and have an idea what kind of data it has. Okay, so you can see that this code is very simple. I write it in a more flattened way, which means I don't construct some function and some class like the example code did. This one is more suitable for exploring data, although it is certainly not good for production code. But by flatten the code into a notebook, you may have everything in your control. So that is also why I use the queue, because since I put everything flattened in the first level, so you have a lot of things need to be handled in this level. So you don't want to have too many things that the same time. You want to have as little things as possible. So I use a lot of already provided utilities. If there are something that is already provided, I will use it instead of control one that by myself, because in this code set I have to flatten it. So we have too many things in this level. Okay, so anyway, so I'm using DQ as a contrasting block that is suitable for this style. You can see that I'm also using a default counter without renaming the default dict into a language model. Also, because I don't want extra things. So, but I'm also using a default dict and a counter because this is certainly the most suitable tools in standard Python libraries that can do the job. Because I'm running this possible very large data set, so I'm using also a good idea to using a progressive bar to kind of monitoring the progress. Because sometimes if the loop is very large, it may take a lot of time. So you might have a hard time to decide whether or not to interrupt the loop if you have no estimation of how long remains to run this loop. Okay, so let me clear this one and run this again. So it should have a progressive bar. Okay, it should. Okay, but it seems the progressive bar doesn't work very well right here. I'm not sure why. Probably because this one, because I'm using multiple notebooks on this running environment, so that might make some trouble. But when it works correctly, it will show you a progressive bar. So let's see how many keys do we have. Okay, so this one is a little bit broken, but I don't want to close this tab because I already trained a model, so that's why. So but anyway, what I can do is to do this thing, or to list the first 10 elements. Okay, so because the order is 10, so we have a lot of tuples, a lot of strings of 10 elements. So these are some of them. You may observe that it has some patterns right here. This is because in Python, the dictionary, the standard behavior, the behavior of Python dictionary is an ordered dictionary. So the keys is ordered by the time that you have added this key into the dictionary. So this should be the first cipher keys that is appended or insert into this dictionary. So you can see this one is because this one is the first like 10 characters in the first sample, and this one must be the second to the 11th characters in the first sample, and this one is the third to the 12th characters in the first sample, and so on. So you can see this pattern. So how about so how many of them? Maybe I can just use the len to see how many of them. So the 10 tuples we have like 1, 2, 3, 4, 5, 6. This like 1 million, 1.6 million tuples. So if I change our tuples to be something like 9, the numbers are going to be different. So okay, it has some trouble for showing the output, but you can see okay, still have some final result right here. So if we are considering using the Markov chain of order 9, then it has still have over 1 million tuples, but a little bit less than the case when we have n equals to 10. Okay, so how about do the sampling? I still construct a function that do the sampling by using this counter. However, you can see the length of this code is considerably shorter than the example provided by that is discussed in the lecture video, because I'm using random choices. So all I need to do is to simply, I can put it into a one-liner, because I'm just giving it a name, which is the default argument name of this method, random.choice, this function. So I'm giving it the proper name. If I don't do that, I can simply just put this guys into here and this guy into here. So we'll have a one-liner. So this one is basically calling the functions right here. The only reason that I need a function is I can convert the counter. I can construct argument from a counter. And that's all. This function. The hard work is done by this random.choices. Okay, so for example, I can simply use the choices again because this one is so common. Is used so common. Random choice, random sampling. They are used so common. Right here, I'm just using choosing a randomly initialized. I'm choosing a initialized sequence randomly. So for example, let me show you what this S0 is. This MED by PR. I can use this one as well because all I need to do is something that is a key of the dictionary. I can use this one as well because all of this or this one, because all of these are some keys in the info. The info is all the information that I do the correction. Actually, the info is the language model itself. If we are using the terminology of the original notebook. Okay, so I choose the random one, which is MED space by space PR. So I make my sequence as from this initial sequence and generate 1,000 characters. Okay, I generate 1,000 characters from here. Okay, so you can see that all I do is I choose the last n characters from the generated sequence, and at the beginning it is just the sequence itself, because the S is initially set as S0, and S0 has a length of n, so it is the S itself at the beginning. But we are going to append this sentence a little bit, so this is going to be longer and longer. So we always just pick the last n characters. So if k is not in the info, just be careful. Just by make sure everything works just right. Because the way I am doing it, almost And because this is just a simple demo, so I probably don't need this one. But just to be careful, so I put this guy to deal with a case that K is not in the info. So in this case, I'll just simply break the loop and stop the generation. So other than this one, I'm pretty much in most of the time, I'm pretty sure that K is in the info, because it's we have start from some key and generate something characters that is appeared in some of the sample. More likely than not, because every sample is the length of every sample is like 10,000 or so. It is more likely this one becomes an initial sequence of another what I should say is there's another character after the character that we just appended. So it should be in the dictionary most of the time, unless it is going to the very end of the paragraph of a sample. So this usually would not happen. We are going the loop will usually stop when the length of s is equal to 1000. So anyway, I will use the about sample function to sampling one characters out of the counter and append this character to the end of s. This one is a little bit inefficient because we are concatenating one character at the end of a string. This one is expensive. However, this one is shorter, and there's some more efficient way to do so, but I'm not caring about the efficiency of this part because this one is very fast. If this part is in here in the training is more time consuming, so I'll be more inclined to sort of optimize or writing it in a more correct way. But here is just a demo, so I'm writing it in a more inefficient way. All I care is I will see later. So let me just do the generation. So you can see this generation is a little bit like something you might can see in an academic paper. Let me do it again from the same initial. You can see that is from the same initial, but this time we have a different text generated. So our model is kind of creative, and you can see we have a DC GAN and W GAN and FHQ, which we'll cover in later in our this course, because GAN is one of the famous generative models, so we'll cover this one. So let me do it again, and we have yet another different text generated by this initial prefix. Because this was an academic paper, we kind of expected that there be some word that we don't recognize, because there are a lot of different terminology in different areas. So we may have, so they may be legitimate, but because they are just in some special word, in some special terminology in some special areas, so we do not understand. So this gives some advantage of this model because it can generate something wrong, but gives us some impression that is some terms of certain academic field. So for example, I don't know what this word looks like a wrong word, but maybe it is some terminology, especially there is a dash here, so it might be some terminology. I'm not sure. Maybe this one is a real word. Maybe not, but I don't know this word. And what is HSP90? It may be something fake, or maybe something correct. I don't know, because I have never seen this one before. But what I know is, I know this again, and W again, FFHQ is true word, it's a real word. I'm not sure there's actually a point finder, but judged by this again, W again, and the FHQ, I am sort of thinking this is possible to be a real name of an algorithm. Okay, so when doing a demo, I'm more care about something that is the output of the thing. The reason I'm using a markdown right here is because if I simply put S here, the line would be too long, so it would be very difficult to see a result. Even if I use a print S, it is still too long. So although I have to put more lines right here to import more modules right here, I'll choose this one because it will generate a better output. The performance or efficiency is not the top priority for this kind of code. So if I really want to make it more, say, more efficient, then I might want to be doing things like this one. I don't know. So maybe I put it into a list, but I still let me copy this cells to another. So I'm just give you example of how an alternative way of writing this kind of things. So maybe I should do, what I should do is to make it as a list. So when you put a list right here, it will become something like this one, because it treat because string is iteratable. So if you fit any iteratable into a list, it will become a list and iterated, and the element are the element iterated over the object. So in this case, each character, when I iterated over a string, each time you will get a character later. So that's what we get for this tuple. So let's make it a tuple, and in this case, this one still works, and the thing does not work here is we probably need to put them together, join them together. And right here, you can simply using append C. That will be just fine. So although we still need to do some string operations right here, it seems no point, because we are doing string operation right here, and then we still do. Although we eliminated the string operation right here, we still have to do operation right here. The thing is, this one is usually considered to be more efficient, and the thing is, S can be a very longer string, and the K is just a constant length. Because I mean this one has to be a length to be n equal to n. So on the contrast, S can be longer and longer. The efficiency will decreasing when S is getting longer and longer. So we can actually control the damage. So that's why this one is much better than this one if you consider the efficiency. let me try to do that. Okay, replace. I do a replace. Okay, here I will convert S to an. I do this at the final to join it again. So this one is pretty much the a very common pattern when do the programming. So, but you can see that you can feel no difference because either way they are running very fast. So that's why I don't really care about this guy. If this one is longer than 1,000, like 1 million, I might have some thought about this, or at least I will consider. Maybe if it is 1 million, maybe I will simply go this one. But 1,000, I don't really need to worry about too much about the efficiency. Because that you cannot actually feel the difference. That's still the same thing. Okay, so this one is a simple case. So the reason I'm providing this example is to show that you can write the algorithm very, very differently. Because if you have only see the example notebook that is given in the lecture note, lecture video, I mean, and you can find a link in the lecture note and maybe in the slide. If you have only see that, you may think that, okay, what can I do? This is only one way to write this algorithm, because it seems so straightforward. And you might think, even if I write by myself, it should be pretty much the same. The fact is, there are many different ways to write a code. So that one is just simple one way, and you can write in different style and different order, and although the algorithm is pretty much the same, and I actually use the same data structure right here, the code still can be very, very different. Okay, I use the same thing to here to write STM model. So use the same method to do the same computations. The only difference is that let me try to run it a little bit. So the strange thing is that I could not find the progress bar again. I don't know why. There should be a progress bar. Okay, so let me do the first 1,000 samples from the dataset, and I actually load every sentences into the text data. So you can see the text data right here. Okay, maybe it's too long. Maybe I should just show the first one. Okay, let me just show the first one. Maybe it is still too long. Show the first. Oh, okay, it shows right here. So this one is the first data. So I collect everything, every sample, the text of every sample into a list. Text data is a list. So the reason I need to collect this is because I need to build a data pipeline for my PyTorch model. So I'm using PyTorch Lightning as an example. You can use Keras or PyTorch, vanilla PyTorch, or TensorFlow or JAX or any other, or maybe if you wish to write it into NumPy by yourself. I don't think that would be likely to happen. But some popular choices are PyTorch, TensorFlow. Some people like JAX, and the Keras. If you are using TensorFlow, you really can consider about consider about Keras. Keras is very, I think it's very good for learning. Still one of the best framework for learning, deep learning. And if you're using PyTorch, I'm using PyTorch Lightning, which is still have some share some properties with Keras because they are easier to learn and easier to build and easy to use. Okay, so after doing collecting the information, I collect everything in the character information in this counter. You can see that I can see which one is how many characters do I have. I have this number of characters for only the first 1,000 samples. They are not just 100 characters, 200 characters. They are actually like it collect like this many of characters. But which one is the most common one? At least the first common. Let me first list the top 10 most popular, first most appear for the most times, most frequently characters in this one. The most frequent one is the space, no surprise, and the ETIAN. That is aligned with the common sense, and so on. If we list like more like 100 ones, you get something a little bit stranger, but very common in like academic papers. Like you can see the pi, the arrow. This might be a symbol of degree, and some operators. If we go further, like 500, I think, you can get something kind of weird. Still some symbols, but less common, and some strange Unicode symbols which may not be parsed correctly, or may have some spatial usage. So how many characters exactly? For now we only have like 600 different characters. Although we have like 3 million characters correct, they are all false in this 636 distinct types or kinds. So what if because 600 is still toward the large side. If I want to build a model that do the classification, like output the softmax output and using some cross entropy, 600 maybe towards a little bit towards a large side. So I would think that a lot of the characters are either we parse it error or it appears very unfrequently. So maybe we can just kind of ignore it. So what if we just use the first 160 most common characters? So how much characters are going to be ignored or discarded? So what will be lost if we are only using the first 160 most common words? The thing is, we can do using Python to calculate the information. And so you can see that there are only like 2.6 out of 10,000 characters are missing or ignored if we only consider the first 160 most common characters. If we are using like only 100, we still got like a 99.8 coverage, almost 99.9 percentage of the coverage of all the characters. They are only like less than 1/1000 information is going to be lost if we just simply ignore them. And because I already also collect the information of how long of each sample is, because I have really no idea how the samples look like. So I also do the collection So to see how long each sample is. So mostly you can see a lot of things is like I can actually find the minima, the case, and we can find the minima of it. Okay, I actually do this right here. I use the numpy actually to find the maxima. The longest the paragraph in a sample is like 135,000, and the shortest one is like 3,000. But most common they are you can do to find it out, but most of them we can find say like the average like 30,000 characters in each sample, and I can also do the median. It doesn't have median. It actually has a quantile, I think. Per okay, no. np.quantile. I can do this right here directly. Median, it has median right here. The median is a little bit less than the average. It's like, but it's still almost like 300,000. Okay, 30,000. Okay, 30,000. Also, the mean is also around 30,000, but a little bit more than the median. So anyway, I'm going to construct the data pipeline right here. Okay, so I already recorded for like 1 hour already. So this one is just okay. So I'm using some like LSTM as a building block. So I was using this as a demonstration of how this cell works. So if I have something like it looks like you can see that I put this one. This one is a batch size. The first one, I have a batch of 1 sample, and 300 is the length of the sequence, and the 32 is the number of features. Like for each samples, what is the dimension of each element? So we have a sequence of length of 300. And for each items or element in this sequence is a vector of dimension 32. So then we construct it. I construct it as a tensor of a PyTorch tensor, and we can actually feed this into the LSTM and get an output. The output has two elements. We can actually do. You can see the output has actually 2 elements right here. You can see it has 2 elements. The first element is the output of everything. So it still has 300. It is the output of the sequence. Also, it is a full output, and because our input dimension is 32. And output dimension is 128. So instead of 32, it becomes 128. This is the hidden state. The output of everything. However, if you like the LSTM has some hidden state. Output 1 is the hidden state. Output 1 is a hidden state. So the first one, you can see the shape. At least 128. This is the first hidden state, and because it has it's actually it's a long-term memory, and it has actually the short-term memory, and it has also the cell memory or cell state, which is this one. it is also has this kind of size. So you can actually run it in a loop because you already get the hidden states, and you can feed these states into the next cell. So let me check. Okay, I forget. You should have to put in the two of them, or maybe I should put one. I think this one is the case. So if you put this one as the second input, it will treat it as the hidden state. So you can run the LCM in a loop, just like what we are supposed to use it. But in general, because we are going to training, I'm not using it like this way. I'm trying to use it as a building block, as a model. Okay, so then first of all, I'm trying to build my data pipeline in PyTorch. So PyTorch Lightning also use the standard PyTorch data pipeline. I'm considering a sequence number, sequence length of 32. This is because I'm trying to, for the sake of training efficiency, what I'm trying to do is to feed a batch of data for training. So although LTM can use any length of data, but by considering over training, the setting is I'm treating it as a Markov chain of order 32, just like a Markov chain, like an n-gram model, maybe like a 33-gram model, but or in another word, it is a Markov chain of order 32. I'm just using it affected like a Mark chain of finite order, not using the full potential of the STM, but in practice it works fine. Because our model is not powerful, so it does not look that much. We do not lose that much. So I'm trying to use it, but by any means, you are able to use training data with different lengths, with vary lengths. Like sometimes it's length like 32, 10, and sometimes it's like 100 in any length. But what I'm doing is trying to do it in a fixed length, so that it can be trained efficiently. This is a common way of training LCM, but it has its own disadvantage and advantage as well. But this is not the only way. But anyway, I need a length to be defined. So and also I'm using a special character called the end of sentence, and actually I call it the start of the sentence, but I just call it start for padding. And because I'm pretty much fall into the framework of Markov chain of order of a finite order, so I have to do the padding. I'm expecting things to have the fixed length, the sequence to have the input of a sequence to have a fixed length. So if the sequence is shorter, I'll pad it with the start. Okay, anyway, so this text data will output a sequence of lengths exactly the 32, and the character right next to this sequence in the training data. So in PyTorch, when you control a text data set, you are kind of giving it initial. You only need to give it three methods. One is initialize, of course, and the length. You have to provide the length of this data set, the information of the length of the data set, and You only also need a get item to get the item. So it kind of look like the list, sort of like a list. However, it will be very difficult to pinpoint every slice of the data. So it might make it more difficult because we have like 3 million characters, and each sample is not length equally. So if I wish to find the say the 122,000th character exactly, I have no idea which sample I should pick. I could build a data structure to record the length of the accumulated length of each sample and do some algorithm to find it, but I didn't bother to do it. The way I do it is I simply return the I simply give a length that is sort of have some multiple of the size of the text data. So in this case, where our text data have the length of text data is probably 1,000. I remember, if I remember correctly. Also 1,002. Our text data is 1,002. So I have like 1,002 data. So this one, the length of this data set is like 10,020. And then what happens when I want to get some items? So because this is just a multiple of these lengths, so when you have an index, I simply find the remainder to divide this index by the length of the text data. So I can actually sample each sample of in the text data equally, have equal chance. So it is arguably that if a sequence is longer, so in our example, the longest one is like 300,000 also, and the shortest one is maybe just 3,000. So we might have give a more chance to a longer sample and give less chance to a shorter sample. That might be more fair, but this is just a simple, quick experience. So I didn't bother to do that. I give each sample the equal chance. I can do the weighted sampling. So obviously the weight is the length of the length of each sample. So I can actually do the weighted sampling. At the PyTorch, actually, there is a PyTorch. I think there is a PyTorch support for weighted sampling, but it did it not efficiently. So but still, I can simply use the random, because I'm using Python. I'm not using PyTorch function right here, so I can use simple like a random dot choices, just like I did before. However, I just didn't bother to do it. So if I really want to do it, it is not difficult. But for the current implementation, I'm choosing to do it so that each sample have an equal chance, not fair, but equal chance to be chosen. So after I choose a sample is chosen, I randomly pick a position from the data to as the, because suppose we have like 1,000 characters, so each one has an equal chance as a output. Remember, we are actually using consider this sequence as a Markov chain of all the, say, n or all the n. So each one has an equal chance, except one more character. We are giving one more character a chance. That is the end of the sentence. So if we have 1,000 characters, so this one is chosen one random number from 0 to 1,000. So if 1000 has been chosen, the output, the target, is the end of a sentence. Otherwise, it is simply the character. Then when I pick the say 30, suppose let me just 32. I pick the 32 characters immediately before the character that we were just chosen. So if there are not enough characters to be chosen in the sequence, I put the padding. So I put a lot of start in front of it. So in fact, this one is not efficient. Just like we said before, this one is a plus right here. But this one has a fixed length. So although it is inefficient, probably I should construct a list first and do the extend the list. It might be a little bit efficient, but since this one is just fixed length, and still these two are list, so I can tolerate this little inefficiency in change of the readability of this code. So okay, so this one is a padding, and then you can see that even though the pad length is 0, this one just do a simple calculations, and even though if the pad length is 0, this one is still has to do the start and times 0 and plus this thing. So it is definitely not very efficient. But just I say, I choose the readability over the efficiency. This might not be the best choice, because like the reasoning I gave before, this one is in the training. However, by considering the most time-consuming part is supposed to be the training itself, the backpropagation and the optimizer itself. So that is part of the reason I choose the readability over the efficiency. But I can imagine people have different opinions on this one, and I'm actually not sure this one is the best choice, but that is what it is right now, and I have consciously consider different options when writing this kind of code, though it may not be the best choice or best possible decision, but I do constantly, consciously aware of what there are many different choices, and I choose what I am choosing. Okay, so after this data set is constructed, we can build the data set from the actual data itself, and we can do the data loader by convert the dataset into a data loader using the standard PyTorch data pipeline paradigm to do so. And this one can easily do the shuffling for us and do the batching to put simple samples into a batch for us. And it's actually, if we have something that has a variable length, then it might not be. I'm not so familiar with the data loader. I'm not sure the data loader can handle it. Maybe it may not be able to handle it, but at least for this case, this one is pretty easy. The way I know to deal with the various length data is that we do the batch ourselves. We can control dataset that do the batch by ourselves. But for the case right here, we simply use the convenient utility data loader right here. Okay, so this one is a simple LSTM network. Actually, I use a GRU here. I'm not sure. Do I have a LSTM right here? I don't. So I haven't saved it correctly. Okay, so anyway, the let me show you one example. Let me show you one example. Data set right here. So DS0, let's see. So actually, we convert each one of the character into a number, and the first three are reserved. 0, 1, 2 are reserved to a special kind of character like unknown, start, and end of sentence. But in general, each character is converted into let me put this. Each character is converted into a number, an index number, so we can convert it forth or back, and because we are ordered the character by their popularity, their frequency, so you can see that we can see a lot of small numbers like 3. 3 is the most popular. Actually, is a space. We have already seen that. You can see this one very often. So that's not a surprise because the small number are more frequently seen. So you mostly see the small numbers. And because of each number, these numbers are just integers. They are not actually a tensor vectors. So by feeding it into a neural network, you have to convert into each index into a vector. So sometimes you do it by using one hot, but more sometimes you have training and embedding. So in this case, we are training and embedding right here. So you can see embedding. This embedding takes a sequence of this index and convert this a sequence of integers into a sequence of vectors. So the embedding is a trainable weight, and this weight is actually a lookup table. So by using this lookup table, I can see, okay, so number 5, I can pick the vector number 5 out of the copy the number the vector number 5 out of the lookup table, and I can check out the vector index with number 7 out of the lookup table and combine them together into a new sequence. So that's what the embedding do. And after we convert this sequence of integers into a sequence of vectors, then we can use it as an input of the GRU. So that's our second layer, is a GRU, a gated recurrent unit. And after we get the output, we simply get the last one. Because the last one is still a vector, and the vector is not what the vector is does not have the size that desired. The size we are desired is a vector of size of 160, because we're going to output a probability distribution, just like what we did for the classification. For the MNIST, we have 10 outputs. For this one, we have 160 outputs. So we have to output a vector of the size of 160. So we do a linear to do so. So by combining all this one, so first we got the input. This one is a sequence. Then we put it into embedding to convert, to translate into a sequence of vectors. A vector of what I choose is a vector of size 32, and feed it into a GRU and get the last one. Actually, hidden state. We don't need to get the full output. We only need the last one, and not the cell state. We need a hidden state, H right here. So H is the first element of this hidden state, and then we feed this hidden state into a linear layer and get our output. Because we need this linear to make it into a correct size. So the training is simply get our output and do the cross entropy to compare cross entropy cross entry is actually just the y hat is our prediction, and the correct y is just a number. In PyTorch, the cross entropy loss can deal with all kind of input. When I say all kind of input, I mean it can be an integer that it represent the index of the things, or it can be a one-hot vector. So because they have different dimension, the PyTorch will deal with it without any issue. And finally, you give some configuration of what optimizer and learning rate or something you need to provide it. So that's all. So for the first two parts are just standard PyTorch module, and you only need to provide some training step and training configuration, mostly optimizer configuration, and that's it. That's it. And by constructing the models, we can simply use the train.fit to get everything we want. So this one is this one can show the generative code. However, I am not running this model right now. What the model I'm running right now, I'm also using the same models on a different dataset, which is like some novels in Chinese. It can also generate some reasonable, good text. Though I think Chinese, because there are more Chinese characters than English characters, you may want to have a much larger dataset, no matter which kind of algorithm you are going to use. But another model which have the same data pipeline is right here. Is that I think I still got this model. Let me check really quick. Okay, still that's the convolution. So if you are not familiar with the RNN and or maybe not comfortable or confidence that you can handle with RNN, it's okay. Because you can use any like MLP, like you can just use a bunch of linear and has a simple model to do the same thing, because we already have a fixed length of the sequence. So you can simply like here, you simply flatten the input and treat it as just one big giant vector and use MLP to do the output. That's still okay. You don't need to have a perfect performance on the model. Just try to. The important thing is you have the pipeline and you know how to train the model. That's all. That's the major point. I wish that you can already prepare it. So this model is a little bit complicated because I'm using sort of like a gated things. So I'm using convolution 1D on the sequence. First of all, I'm still using an embedding, but I'm using two convolution 1D to get two output, and one is used as a get and the other as a content. I just like a gated convolution, since I put them times them point-wise together and get an output. Then I feed these things into a several like a view, like a little. I kind of forget what. Maybe I just put it into a little one. Okay, I put them into. Okay, the first one is used to for the get. This linear is for the get thing. So so it is a little bit complicated. Okay, the get is a little bit complicated than the gated convolution things, because I sort of have some idea of designing this one. So I sort of find the way to compute, not only I get this content, this sequence content, I also use a linear layer to aggregate all this sequence into one single vectors, and use this vector to do the multiplication, I mean the dot product to every single vector in another sequence, and then use that one as the gate. So a little bit different mechanic right here, but the idea is that since I'm only wish to generate the next character, so I'm trying to find out which part of the sentence is correlated to the last one, or at the tail of the sentence. So only need one thing to check the importance of each point of the sentence. So I only need to construct one vector and use a cosine similarity. Actually, I'm not using cosine similarity, I'm using dot product. So I use a dot product to decide which one should stay and which one should be ignored. And that's it. The reason that using a convolution 1D at the beginning of the sequence is by using the embedding, we only know the meaning of each character, but each character is kind of working with the surrounding characters. Like we usually has like a th to combine together. So the h alone does not provide enough information. We probably need the character surrounding with this one to give more meaningful information of this character. So by using convolution 1D, we can get things like this one. And I'm not using a too large and too small window. I suspect that the next three characters and the past three characters are important. So that's all I use. I use it for each character. I consider this character and the relation between the first three, the three characters next to it, left to it, and the three characters right to it, and consider a new meaning of this character. And I choose a little bit larger vector because I am imagine that this information, the embedding only has a dimension of 32, the length of 32. Then so because we only have 160 different distinct characters. If I'm using a vector of length like say 200, I might just use the one half vector, because one half vector can has only the length of one half vector is only like 160. It is shorter than 200. So I must have some vector that is shorter than 160. So that's the embedding length. So the embedding length I'm choosing is like 32. Because this is considered only the meaning of this character alone. So when after this convolution 1D, I'm considering this character and how it interacts with the surrounding characters. So it will have a longer dimension. So it's more reasonable to have a longer dimension because we have more different combinations. And after this, we use this information and the vector I just design together and get that we are expecting to, we're hoping that represent some information about the tail, and using this one to have a dot projection to this vector and decide does this vector or something around it matters, so that we can it's useful to decide which is the character to be appear next. Okay, so this is the idea of how to design this architecture. Okay, so this is what I didn't pay too much attention on it, but just a very quick thought on planning on this, designing on this network. Okay, anyway, because one is start of sentence, so so this one here I'm trying to construct a fresh new sentence from the beginning. So by beginning with, okay, no, I should do this one first. So by start from very beginning, because we have a sequence length and all starting since, probably I put it markdown here, right here. Okay, let me do it again to have a prettier output. So this is what it generated. You can see that using this model and the training. By the way, training this model, although it seems seemingly more complicated, it is much faster than the LSTM1. Even if the sequence length is longer. For LSTM1, for the very simple one, it is very fast. But if you increase the dimension, the hidden dimension, the size of the hidden states, and increasing the length of the sequence, when you're increasing the length of the sequence, you probably need to increase the capacity of the model so that it can learn better. But for the case of RNN, it will become much smaller, and in this model it will train. Even if you increase the length of the sequence, it will the training is still very fast. Okay, so this one is something that it generated by this guy. I'm not sure how much. Okay, sequence length I'm using. Probably I should run it again because I was running another notebook. Okay. Okay, we got the right sequence. Hopefully the model is not corrupt by what I just did. So let me run it again. Okay, so here. So this one is market share of order. We are training it for order 32. So you can see that there are a lot of words are correct, legitimate English word, but still it is not perfect. Because we are training it with a large data set and it is not converged yet. But still, you can see that with this short of model, it can generate reasonably good text. And if we can actually provide it, not unlike the case with using memorized dictionary, we can freely choosing the initial word. So for example, I'm choosing it here is trouble of jumping to the okay, how we have here like okay, so let me put some arbitrary initial sentence right here to prove this. So something like seems like a suitable initial for some academic paper. Okay, so you can see that the generated text is to prove this. I don't know what it is. Only in million ATA material and didn't know things like this one. And you can ask something like, how large is the universe? Okay, and we're trying to use it as a ChatGPT and to see what happens. It will not do very good, and there are many issues about it. We'll deal with later in the later lectures in the course. But you can see that how large is the universe answer. It has absolutely no meanings of the correct result. So the thing is, if you try this homework, you'll see that when you have a large data set, you need to have some motivations of the. You have to modify have certain architecture of the network in order to deal or handle the large data set. Not every data set, especially small, not every model, especially small models, does not work very well with large data set. So you may try this thing by comparing the. So you have a few things that you can compare with. The first thing is the simple statistical model. So you can see the cross entropy. You can actually compute the control cross entropy to see which order has which kind of entropy. On the training data, we're kind of expecting that the model to have a smaller entropy by comparing with statistics models with markup models with small order, because when we have a longer context, we have more certainty. We should have more certainty with the next character if everything goes well. If I have a right model. However, you may find that you can try that the model with a small dataset and a large dataset. So let me make it clearly that this is not a requirement of the homework, just a suggestion, or I'm encourage you that you can do certain experiment. You can try a small dataset. You can find a small model, maybe just MLT or STM. STM is fine, and you can try a small model, and with small dataset, it might have a very decent cross entropy and generate some decent text. But when you increase the size of the dataset, use a larger dataset, it may perform very poorly and doesn't generate some. It performs poorly in both the cross entropy matrix and in the generated text. So if you are increasing the capacity, like increasing the hidden size of the hidden layers, or maybe add a little bit one or more layers, and you have to do it right. There's something you can do wrong, but if you are doing it right, you may find that larger model can overcome the size of a large data set. However, it may have its limit because if it is LCM, it will be going to be small, and if it is MLP, certainly you have a limited size of window, and because the architecture itself, the parameters is going to be growing very fast if you are increasing the size of the length of the sequence. So there are some issues on this architecture. That is what we are going to focus on later, on what actually happens to large language models and what things they did right for the designing of architecture so that it can handle more and more data. Okay, so that's all, a little bit longer than I expected, but that's some description and discussion on how the homeworks, some issues related to homework, and I hope you can all enjoy and do the homework well.